In this video, we'll be discussing atoms, ions, and chemical bonding. Now, as part of a typical physiology class, this is a little chemistry heavy. However, it is still knowledge that's going to be helpful when you get into the topics of membrane transport. As we know that the structure of the membrane really dictates how we breathe things across that membrane by diffusion or active transport or osmosis. And the type of transport needed is going to be dependent on the structure of the solute being moved. So we're going to use this information, not necessarily as direct information as relevant to you as a chemical topic, but as background information that will help you determine which method of cellular transport we're going to be relying on later on. So we start with looking at the structure of an atom. We look at an atom as having a nucleus composed of positively charged protons and neutrally charged neutrons. Surrounding that nucleus in circular orbitals, we have our electrons, negatively charged particles, and we will always see in an atom the number of protons equal the number of electrons to cancel out and give us a neutral structure. This atom is going to be the smallest unit of the chemical elements, and it's this atomic structure that we're going to see represented on our typical periodic table of elements, with the number of protons giving us our atomic number at the upper right corner. So when we go back and look at our exact model that we just had a couple of slides ago, how many protons do we have? 1, 2, 3, 4, 5, 6 protons. Looking for the atomic number 6 on that periodic table, we find it right here. So our mystery atom that we were using as a generic example happens to be carbon. 6 carbons, 6 electrons arranged in circular orbitals around that nucleus. Now, when we look at the orbital structure, because we're going to get into the formation of an ion, that's what we have to look at. When we look at the orbital formation, in small atoms, we will see our nucleus containing 2 protons, and we will see a single circular orbital containing 2 electrons. That's as many electrons as we can store in that first circular orbital. If we want to go to a bigger atom, it's going to hold more protons, therefore hold more electrons, we have to increase the number of circular orbitals we have. So we look at carbon again, and we see our protons, number 6. We have our first circular orbital, only able to hold 2 electrons. But we have 6 to put in there, so we have to add a next second circular orbital to put the remaining 4. As we see our atoms go up to nitrogen and oxygen, adding 1 more electron to our outermost circular orbital. Once we get past oxygen into sodium, chlorine, and calcium, the number of protons exceeds the number of electrons we can even put in our second orbital. The inner one held 2. The second one can hold a maximum of 8. Any more than 8 in that second orbital, and we have to add 8. So for sodium, for that 11th electron that had to go in there to cancel out the number of protons we had to add a third outer valence orbital level for that singular electron. Now, when it comes to ions, it's this outer valence level that becomes most important. We will always strive to have a full outer orbital level, a full valence level. That's where these entities are going to be most stable, and that's where these entities are going to be most happy. So we see with chlorine, its outer level has 7. A full outer level would have 8. That's what it's going to want to accomplish. So it's going to accept an electron from a donor, put it into this outer level, and fill it up with 8. Now it's going to be happy. But now we also have an imbalance between the number of protons, which are positively charged, and the number of electrons that are negatively charged. 1 extra electron than we have protons gives our entire ion, our chloride ion, a negative charge. When we look at sodium, we see we have a first orbital level containing 2. We have a second containing 8, so it's full. That lone electron that had to be added for sodium had to be all by itself in that outer valence level orbital. it's going to strive to have a full outer valence. Now, rather than add 7 to that outer valence, it's easier for us to simply lose that electron. We lose that singular electron in the third orbital. That orbital goes away, and what we're left with is the second orbital now being our most outer. It's already full. That makes sodium very happy. But now we have that imbalance again, but this time with one extra proton than we had electrons. One extra positively charged proton gives our sodium ion a positive charge. Now, when we talk bonding, it's all about how two atoms come together and interact with one another. We can have ionic bonding, which would be a negatively charged ion attracting a positively charged ion, as those opposite charges attract each other. We see that with, again, our sodium and our chloride. We get an attraction of oppositely charged particles and an electrical sort of bond, an affinity for one another, if you will. In covalent bonds, we don't donate or accept electrons from other atoms in order to fill our valence level. What we do is we make the best of what we have and we share. So when you look at carbon dioxide, we see that carbon in its outer level had 1, 2, 3, 4 valence level electrons. It would love to have 8. In oxygen, we saw that it had 1, 2, 3, 4, 5, 6 valence level electrons. It would love to have 8. So we bring these atoms together and we share, and we kind of pseudo-fill that outer level. By sharing, if we go around the outer level now and do a full head count, we will see that we have full outer valence levels. We count around the oxygen, 1, 2, 3, 4, 5, 6, 7, 8. We count around the carbon, 1, 2, 3, 4, 5, 6, 7, 8. Now, we didn't increase the total number of electrons we had if these 3 atoms were separate. But by sharing, we still pseudo-fill the requirements it takes for full outer valence levels, and it does create a stable situation for this molecule to exist. Now, if we're sharing electrons, anybody that has more than one kid knows this, sharing equally doesn't always happen. So we see certain atoms have a greater affinity for those electrons than the partner that it's sharing with. So the electrons doesn't get shared equally amongst both of those atoms. Instead, the electrons are held closer to the greedy atom, the one with the greatest attraction to them. That's going to be a concept called electronegativity. It's the attractiveness that an atom has for those shared electrons. So if we look at water, and we look at the bond between the hydrogen and the oxygen as a covalent bond, those electrons are going to be kept closer to the oxygen, and we call this situation a polarity. We have an electrical situation where there's a polar vector along that bond, oriented along that bond, in the direction where the electrons are kept. So we see one polar covalent bond along that axis. We get another equal polar covalent bond along this axis. They give a summation effect, and it will give us an overall polarity to the molecule in this vector right here. Now, not all covalent bonds are polar. Sometimes the electronegativity difference between those two atoms is close enough that we don't get any polarity of either of the bonds. Sometimes, however, we can have polar bonds, but because of how we get the atoms oriented three-dimensionally, each individual polar vector may cancel each other out to give an overall non-polar molecule. Hydrogen bonding is going to be an interaction based on electronegativity, but not within one molecule, but rather with a neighboring molecule. So we look at water. The polar bond of the O and the H is going to have an affinity with its counterpart on a neighboring molecule, giving some degree of affinity and attractiveness. We will see hydrogen bonding getting formed when molecules have hydrogen bonded with oxygen, nitrogen, and fluorine. That large electronegativity difference has an attractiveness for neighboring molecules that has an equal characteristic. Now, when we think about the relevance of this information, again, in most physiology classes, This information isn't presented for you to learn the chemistry. It's presented to give a framework on which we can predict transport into and out of the cell. When we look at the phospholipid bilayer in the chapters involving membrane transport, we know that the middle of that membrane is extremely hydrophobic, water-hating. But we know the watery environments, intra and extracellular, are very hydrophilic. We have a polar bond. That's going to be hydrophilic. If we have a nonpolar covalent molecule, that's going to be more hydrophobic. Any of the ions are always going to be hydrophilic. Now, when we look at diffusion and transport into and out of a cell, two characteristics come into play: the size of the solute and the polarity, or the hydrophilic nature of the solute. If a solute is small and nonpolar, it can drift directly through the membrane without any facilitation or help. Small molecules like carbon dioxide and oxygen are great examples of these. They're small enough to fit between the phospholipid molecules, yet they're hydrophobic enough to not get repelled by the fatty acid tails that's in that inner structure of the membrane. If we look at a molecule that's too big, like a glucose, mostly nonpolar, but too big to fit through the openings in the phospholipid membrane, so it's going to need a facilitated transporter. If we look at something that's very tiny, like a sodium ion, it may be small enough to fit, but it's so hydrophilic that it's going to get repelled by the fatty acid tail inside the middle of that membrane. So it's going to need a facilitated transporter. So now that you understand the information involving the solutes and what makes them polar and what makes them nonpolar, as in what makes them water-soluble and not, watch the video on membrane transport, and it will get into the different types of transport that will accommodate these particular solutes. Thank you.